As a default.
Set
you can see here they have lots of very strange things.
Oh.
Yeah, I actually do not really know what happened. Now it seems to be okay, right? But sometimes they pop up with something very strange.
Yeah,
it's okay.
Tech services kind of and they don't really tell us what they're doing.
Okay.
But your TAs are in the control room. I showed them.
Yes.
How to
Okay.
So,
Great. Thank you.
you.
Thank you. Okay. Good morning. First thing I should say is we have a very large crowd on the waiting list. I counted it's over 60 people on the waiting list. So whether we should open a video-only session, that means you can only watch a video, there is a possibility. I'm discussing with the department. So for anybody who are still on the waiting list, first I should say the waiting list people, if you want to come into the class, you can come, but you have less or lower priority than the student who officially registered. It simply says, if you really want to come to the classroom, you can sit in the corridor or you can stand behind, but you should not take the seat. Okay? The people who register has higher priority take seat. Only after a few minutes, when the class already fill up, you still find some empty seats, you can take it. Okay? So that's a general rule. And for those students who whether eventually, the so-called eventually probably will know it in the second week, will be able to register with a video-only session. There is a possibility. I'm negotiating with the department. Maybe they can open up so you can register as video only. The only thing is video only has lower priority on taking seats in the classroom. Okay, so you should know this. Okay, so now let's start our lecture. Last time I mentioned we got the first lecture is brief introduction of data mining. Then the second lecture is we get into the data in a little more detail. So the lecture, you probably can see I use the same logo or the general panel. For the first one is the top part is our UIC campus, the quad. The lower part is our computer science department building, right, Seaboard Center. So for anybody, video only, you probably can see it anyway. I usually, for each chapter at the beginning or the end, I show some pictures. The picture usually I took in different places. This one is a national park. Anybody can guess where it is? This is a little south of the Yellowstone called the Grand Teton National Park. You get huge mountains. Those are the picture. Okay. Of course, we get mountains of data, right? So we have to handle. So to study data, so first we want to know what are the data format and how we can, clean up the data, can get data into detail before we do mining. Okay. So in this chapter, we are going to discuss 4 major issues. One is data objects and attribute types. Then we'll discuss a little basic statistic description of the data. Then we will show you how to do data visualization. Then we will discuss about the measures of the data, especially on similarity measure of the data. The first thing is we know there are lots of data. You already seen it as a computer scientist. You probably know a lot of different tables, different kinds of data. The first kind of data is record data. Record data means usually you may see them, for example, in the relational tables or even in the some kind of crosstab you show in the Microsoft, those kind of different software. You can show pie charts, bar charts. You also can see tables. So the very popularly used data sets, which are somewhat structured, are the record data we call relational tables. Okay, if you go to, for example, Walmart, or you go to university registration system, you will see lots of data like this. They got different relations. Each relation is a structured table, but they have links. They have the keys and foreign keys. They link together. If you study relational database system like CS411, you are dealing with this data almost all the time. Okay? But we also have data matrix. For example, the numerical matrix, for like rows represent some kind of value, columns represent the other kind of value. So in the center, essentially, is a cross together. For example, if you see this table, you may see some part is some kind of like objects, like this one is a Triumph Pro helmet. Okay, then they get into like England. Likely these could be different, numbers or items sold. You get a USA, you get Japan, you get France. Then you get different items. What are the quantities or something they can write it down. So those we call these as crosstab tables. Okay, if you play with Microsoft like tools, like Office tools, Excel, you see those tables all the time. Okay. There are some transaction data. For example, you go to some Walmart, they give you shop, you get one ID. This could be your transaction, your shopping basket. But in the shopping basket, you may put a milk, Coke, bread, and all the different things. When you print the receipts, they give you a long list. Those lists, you can think each one is a transaction, and all the others are the items. Okay, so you get a transaction data in that format. Okay. You may even get, for example, in document data, if you really want to study document, in many cases, they can give you something like a term frequency vector. Term frequency vector means you get this document. You may have some term. For example, this one is a team, coach, play, ball, or something, score. Then you get different things. This different number simply says, in this document, how frequent, how many times those terms appear. Okay? So that's why we call this is term frequency. Once you get this very long, you may have like 100 or 300 terms. They appear in different frequency. You get this term frequency vector. They look like a table. Even the text data you can transform into tables, like term frequency vectors. And of course, you can get other kinds of data. For example, you get graphs and networks. If you go to Washington, D.C. to take metro, likely you will get a map like this. This is a graph, shows different lines. It have different stations. You go to web, you can visualize the web like this one is visualize the web. Okay. Then you get biomedical things like molecular structures. Okay. Then you can get a structure like this. If you look at social information networks, very likely you want to visualize them. You get a big graph. You get big networks and visualize them as links. Right? So those are another kind of type of data. And the third kind is order data. That means you get lots of sequences. For example, you get a video. The video may show slow motion. For example, you see the players, waving those bats. You see the different parts. Then you actually people may rewind it and replay it. Those are sequence of images. Then you watch the stock. You see those time series like this. Today is going up or going down. You see every minute or every day they form time sequences. The sequence data also can have other sequences, like transaction sequence. Walmart suppose you have a shopping cart, like you go to Amazon. Today you buy this, the other day you buy the other things. They give you a long history. Say last year, how many things you buy was its shopping sequence. Those are the sequential data. sequential transactions. Okay, and if you study genetics, like DNA sequences, you likely will find that, like this one is a human, this is chimpanzee, this different apes or mice. You get all the different sequences. They do the comparisons. Those are genomic sequences. You get lots of order data. Of course, you got lots of spatial, image, or multimedia data. For example, the spatial data could be the maps. Actually, if people really study like civil engineering, you will see the overlay of maps. You may have cities, overlay with highways, overlay with parcels, overlay with some land usage, or even overlay with underground. You have lots of system, dilute the water, pipes. You can overlay many things. Those are the spatial data because they related to the location. And we may have images, videos. You see so many. I will not show it. Okay. But the data has some common characteristics we have to handle. Okay. One characteristic is dimensionality. That means how many dimensions you may have. Of course, it depends on how do you define the dimensions. For example, in the text documents, okay, you can think every term is dimension. Then the documents may contain very high dimension data because you have so many different terms. Okay. But if you think about a relational table, you may have 10 or 20 attributes. You can think they have 10 or 20 dimensions. Okay. It really depends on how do you analyze data, define dimension. But there's one common thing people call curse of dimensionality. That means if you handle 2 or 3 dimensions, maybe easier. But if you handle hundreds of thousands of dimensions, that's a big problem, right? So the curse of dimensionality is a major challenge in data analysis. Okay. Another thing is the sparsity. Okay. You think the data you get a lot, it must be very dense. Actually, once you get a concrete data, you really draw a table. There are many, many empty things. Okay. Just thinking about you register CS412. How many courses we have, how many students we have, how many semesters we have. If you draw a big table, okay, you are not going to take all the courses. Maybe computer science or UIC offers, say, 3,000 courses. Every semester, you can only take 2, 3, 4, right? So the majority is empty. So that's the sparsity of the data. Okay. And another one is resolution. Resolution means how detailed scale you want to analyze. Okay. For example, you may register Walmart transactions down to sub-seconds, but you may not even want to analyze in that scale. You may want to analyze by month or by day. Okay. So that's a different resolution you want to see. Another thing is distribution. The data may be distributed in very uneven way. Okay. The normal one could be like you get a standard Gaussian distribution. But in many cases, it may not, right? So we have to study how the data concentrated and how they spread. Now we look at the data objects. Okay. The object usually is also depends on how do you define the object. Usually, the object could be one particular entity. For example, you can think in the sales database, you may think customer is object, okay? Or you may think item is object. So it depends on different things. But for each one, you may have lots of properties associated with it. Usually we call these as attributes. For example, you get a person, you may have property like age, gender, like a history of the credit or something. So these are the attributes. In relational database, you usually call these attributes or columns. The attributes, in many cases, also people may think they are dimensions. Okay, some people call it dimensions, some call features, some call variables. In database field, they call attributes, but you go down to statistics, likely they call variables, right? And they may have different characteristics. For example, it could be nominal. That means really defined by name, like red, blue, or your last name, first name, those are nominal data. It could be binary, yes or no, on and off, those are binary data. You may have ordinal data, like the data you put in implies some orders. For example, if you get a grade like A or B, those are the ordered data, right? You actually can map them because A is greater than B, then greater than C. You actually know it. Okay. Numerical data is also very popular. We are going to study a little, but numerical data usually defined like an interval-based and a ratio-based. We are going to discuss a little. For example, you say 100 degrees Celsius or 100 degrees Fahrenheit. It's very different from 100 degree Kelvin. The reason actually is one is ratio-based, one is interval-based. Okay. So I'm going to get a little down that you will see. For example, you get a color. Is the color nominal data or ordinal data or something? It really depends on what you are studying. Okay. If you study the traffic light, maybe you can say they are identical. There are three different things. You cannot say red is bigger than green. Okay, so then you can say this is nominal. But if you study physics, you can say the data can be mapped into a spectrum, then become ordered, right? So let's look at the attributes, okay, in more detail. You can see nominal data usually like a hair color. Okay, this is nominal data because you cannot say which one is bigger, which one is smaller. Right? And even the ID, so you can get a student ID. Your ID is smaller than the other one. Doesn't mean you are smaller than the other one by any means, right? So those are the purely nominal data. They are not ordered. Binary data actually has two kinds. One we call symmetric binary. Another we call asymmetric binary. Symmetric means, this yes or no, or these two things is almost have equal opportunity. The typical one is gender. The male or female, these are just equal, in the sense data distribution is very closely equal. There's nothing one is bigger than the other one. Okay, but an asymmetric one, sometimes you want to treat them intentionally differently. For example, you get a medical test. Suppose you want to check whether it's cancer or not. You say, oh, finally it's positive or negative. Actually, positive means kind of a sound alarm, right? Negative, probably can ignore it. So that means you treat them very differently on different values. Those we call asymmetric. Ordinal means you really have an order, okay, like a junior, senior, freshman, or sophomore. You really know there's an order. Okay, like small, medium, and large, there's also order. Right? Then we look a little on this quantitative data. Like we just mentioned, we have quantitative data may have two kinds. One is interval-based, another is ratio-based. Okay. Actually, of course, the quantitative data, you may say they are integers, reals, or some kind of number, but we usually treat them very similarly. Okay. Of course, when you write programs, you have different precision or something that's different. But interval and ratio is different. Interval means actually, when you measure them, they are equal-sized units. You will not find an absolute 0 point. You can say this one is double of the other one. Okay. For example, when you measure degrees, you say the degree is the water freezes at 0 degrees Celsius. Okay, and boils at 100 degree, Celsius. Suppose you get this, but you cannot say the 100 degrees is infinite bigger than 0, because you actually know you heat the water and you start from the ice, finally become boiling. Actually, it's just a gradual process, right? But you do have some kind of data. They really have absolute 0 point. For example, when you define the temperature in Kelvin, or you have a length or counts or monetary quantities, you actually can say, I have double money than you. right? That means you cannot say my temperature is double than you, right? Because it doesn't make sense that it's double. But you say my money is double than you. Simply say you have like 100K, I may have 200K. Okay. We have an absolute 0 point. We may even have a negative point. So those actually we call this as a ratio based. Okay. Of course, you can treat them differently when you write some routines. But you just know there are two kinds of numerical data. Okay. Then we also have discrete versus continuous data. Okay. Discrete means you really have a number, you have certain precision. In the middle, it does not really make sense. Okay. For example, like a zip code. Suppose our zip code is 618.61801. Okay. But you really do not have 61801.3.5.8. It doesn't make sense. So that means those are discrete data. But the continuous data means in principle, you can chop them almost infinitely. So they are, those are really like a real number. You can represent them like a height or weight or even temperature, right? So these are the typical data we know. Then we will see how we should describe the data. We first probably just look at the numerical data to see how we should describe it. Okay. To describe the data, the first thing is usually you will describe the data in two ways. One we call central tendency. That means you get a bunch of data where they are centered. Centered could be like where is the mean, the average of the data, or something we call central tendency. Another one is you want to see how different they spread. Okay, that means whether the data spread is very long, very different, or they focus in the center. Okay, just give you a simple example. In many cases, people measure different countries, whether they are rich or poor. You probably can see the average of their income. But whether this country, the wealth spread is reasonably evenly or is very skewed. Okay, that they look at spread. That means you get billionaires and you get somebody has no money at all. Or whether these two get quite big differences, or whether the distribution is very, very uneven. These we call spread of the data. Right? So we describe data dispersion usually using these different measures. For example, median or max or mean or quantiles or quartiles, outliers or variance. Those are different ways to describe data. Okay. And describe this data, usually you use numerical dimensions. That means the data actually, this particular dimension, all the values are numerical. Okay. And you can sort them. You can analyze them like in this kind of distribution. This distribution typically, for example, this is like a typical normal distribution. It's right in the center, but the others could be a little skewed, and the center may move down to some different places. Right? Now we look at the detailed description in a little formula. I think those formulas should be very easy to explain. Okay. The first thing is, how do you measure central tendency? Where is the center of the data? Like your average income of the country. Okay. The average, mathematically, most if you go to statistic courses, they call this as mean. Okay. Mean, they have sample mean or population mean. Sample means you just pick up n points. The small n, that means the n samples you pick from the whole population. Okay. Then this small n is the sample size. So you want to calculate the mean, you just sum them together, divide by the number of points you sampled, which is n. Okay. That's the mean, okay, or average. That's everybody knows. If you get a whole population, you sum the whole population together, divide by the whole population, you get this mu represented as a population mean. Okay, I think this is very easy as well. But in many applications, they may not want to treat every center just the same, every point just the same. They use a weighted arithmetic mean. Weighted means you put weights on the value. Okay. For example, you can think the weight in the center a little heavier or a little less heavier. Okay. Then you put other data a little in different weights. Okay. You think about this. When we do our class grading, we say homework total is 15 points. Means each homework weights only 5%. But midterm and final weights much more. So finally, you add them together, you can think this is a weighted sum. So finally, you may get a weighted mean, right? So you can see the weighted is also very popular used. Another one called trimmed mean. Trimmed mean is also very useful. Did you watch the Olympics, last 2 weeks? Okay. If you watch those, for example, some kind of gymnastics, okay, those things is very hard to have absolute score. It's not like when you run, you say how many seconds. The judge is very easy to judge. But if people watch you doing gymnastics, there are usually like maybe 7 or 9 judges. What they do? They ask judge based on their own judgment to give a score. Whether it's fair or not, actually some judge probably judge their own country's player. They probably intentionally want to give a little higher score, or somebody dislike some athletes may give a lower score. That's possible. Okay, you cannot, penetrate their mind, right? So what they do is they use trimmed mean. Trimmed mean means they give 9 judges or 7. They intentionally cut off the highest score, cut off the lowest one, then average all the remaining ones. Okay, so this is a trimmed mean. Actually, even for my CS 512, the graduate level course, I always use trimmed mean because I ask the students to participate into different groups. The TA and me, we are going to grade, but we want students to give a feedback as well. They're going to grade. But I use trimmed mean means I assume there could be one student could be a very close friend of the other one. No matter what the other student did, he give the full score, right? And the other one could be a strong enemy, right? So no matter what the student did, he give a very low score. So we use trimmed mean, take off the very high one, very low one, we average the remaining. Usually it's a little fair. Okay, so that's a similar like an Olympic judge. So this is a trimmed mean. Okay. Now we look at another kind of central tendency people want to use is the median. Okay. The median, I assume everybody knows median. The median usually is you sort the whole data. One important thing is sort it. Okay. I remember sometimes I give an exam, say try to do the binning or something. The student did not even sort it. I gave an unsorted, a set of data. They did not sort it, start getting bins. It doesn't make any sense, right? If you don't sort it, many things will not make sense, like histograms, all these things will not make sense. So when you sort it, okay, if you get an odd number, when you sort it, the center one actually, for example, you get an odd number is 5. Okay, the right center, when you sort it right in the middle, that's a mean. Okay, but what about you get a 6 number? 6 number, you get it. You get 6, you get a 3 and 4. You get 2 things in the middle. You have to average the right middle 2. Okay, so this is a mean. But if you get a very large data sets, you try to get a mean. It's a little troublesome. You think about this. Okay, you get either 1 million things. Suppose you go to Walmart, you sell something. You get 1 million items. Okay. You try to find a mean. You sort 1 million every time. It's very troublesome, right? How do you do it? Actually, most people try to get an approximate mean. How do you get an approximate mean? This is a typical way you can see how do you get an approximate mean. Okay. suppose you got a suppose certain disease or something or charges or something. You get things. This is the age you want to get a mean. What is the mean age of of this thing? Okay, you assume this is some kind of, suppose hospital. Okay, you get lots of patients. You want to see the mean age of the patient. How do you do it? Okay, what you do, of course, for this age, they do have 110. Very few people could live that long. But anyway, you get this. You get different frequency. How do you get mean? Or how do you get approximate mean? Okay. Don't look at the formula. The formula looks a little scary. Actually, it's very simple. Anybody can give me an idea how do you get approximate mean? Because these are just aggregation, right? This is 20 to 50. You get this. You just watch it. You guess where is the mean should be. Should be in which slot? Should be in 2150, right? You think why this one, the mean should be there? You think about this. This is something like about, if you add them together, is 950, right? I do not add them, but this is something like 800 or 7 something, right? So the mean must be within this 21 and 50. That's clear. You just watch it, you know the mean will be there. But how do you find this mean? Okay. Because you get 1,500 people, right? And plus this part is bigger, this part is smaller. How do you get mean? You can assume, okay, because right in the middle you do not know how they distribute it. You can assume they sort of evenly distributed. Then you can, interpolating, you can just say, I assume they are evenly distributed. I can plot it, I can calculate, right? So this is the formula to calculate. That means you want to find the low interval limit. That means, of course, you can say this is low or this is low, whatever you decide, okay? Once you get this, you actually can say this is a half, okay? You add them together, how many people together? You get half of them, okay? Then this is the frequency in this slot, 2150. That's a frequency. That's a median frequency. That's a lower one. If you take this low, this frequency should be 744, right? This one minus 744, divide by this frequency, you get it, where they are, then you times the width, you will get it. Okay? If you feel this formula is a puzzle, you go back and think about it. It's very simple, right? So you do not bugged by this. It looks like a little fancy formula. It's very simple. If you derive it by yourself, I think you can get it. Right? So this is just to say, how do you do interpolation? Finally, you can find the approximate mean. The absolute mean, of course, you really need to sort it, but it takes longer time. Right? So now we look at the central tendency. There are some other central tendency measure. One popular use is called mode. Mode means the value most frequently occurred. If you look at distribution, the peak one is the mode. Okay. For example, if you look at the distribution like this, the real peak one, like here, is the mode. Mode is the highest peak. But what about sometimes you may find there are two peaks, or approximately two peaks. Okay. And usually they call this distribution the bimodal. Bimodal means you have two peaks. Of course, you can have trimodal like this. You have 3 peaks. Then you may argue, say the peak is a frequent one. This one is the most frequent. This one actually is not as frequent. It really depends on how rigorously you define the mode. Most statisticians watch this, say this one is bimodal. Of course, rigorously say these two frequencies are just the same. Okay. These two are not the same, but they still call this is bimodal. That means you have 2 modes here, and this one actually is trimodal. But for the unimodal, for the uni one, okay, they usually have this empirical formula. Empirical formula means you say this is a mean, this is a mode, Mean minus mode. Of course, here mean is a little bigger. Minus mode, you get something like this long, right? And mean minus median, you can see this is the median. Mean minus median is this short. So this difference is about 3 times of the other difference. That's the empirical formula. In many cases, it works. At least it's approximately works. Okay? So you just know this is sort of distribution. Okay? Then, of course, in most cases, it's not purely symmetric. Symmetric means median, mean, mode, they all cluster in one center. If you get a Gaussian distribution, standard one, okay, that's actually a symmetric thing. That means that, higher than mean and lower than mean, they are just the same, equally distributed. But in many cases, okay, the mode could be, the shape could be different. Okay? The different means if the mode is lower than this mean, in this distribution, they call this one is a positive distributed. Otherwise, like a mode is higher than this mean, we call negatively skewed. Okay? So you have a skew data in different ways. Of course, if you study statistics, you know as a common sense. For a standard distribution, like a Gaussian distribution, okay, the distribution, usually you got, we have the mean is called mu. Sigma is called standard deviation. Okay, of course, later I'm going to introduce you standard deviation. I assume you know it. Okay. So you got the distance between one standard deviation from the mu, from the real, center one. Actually, is this part we called one standard deviation, this slot. It takes 68% of the data. Okay, but a 2 standard deviation away, it took 95% of the data. 3 standard deviation away, they actually took this whole spread, took 99.7%. That means things outside is only 0.3%. Okay, if something is 3 standard deviation away, is outside, most people call these as outliers, right? Because those are very extreme, bigger or smaller data. So actually, when the data becomes really big, a lot of distribution is normal distribution, standard distribution. So this kind of a distribution, we should really understand it. So then later you try to get outliers, getting, you try to explain sigma and mean, they're like a z-score or something. You can use z-score, to compute this one to see how center they are or how outside they are. It's quite easy. Okay. Now I just introduce a little on this standard deviation or variance. Okay. This essentially try to measure the spread. Okay. Measure how the things are spread out around. You can think about it. If your country's, suppose the income is very close to the center, okay, that spread is very thin. So you may say, everybody almost get the same income. Okay, but if it's spread very far away, you probably say, the income on the high end and low end have a very big difference, right? So the same thing, we call this is variance. Variance computation actually is you get an average, or we call mean. Okay, then you take every point minus this average, you square them. The square them means plus or minus will not cancel each other. You square them, you add them together, then you divide by the number of points. Okay. By number of points, of course, some divide by n, some divide by n minus 1. It depends on the formula. Okay. If it's a population, definitely divide by n. If it's not population, a lot of formula you have n minus 1, right? But whatever, but a very important thing is this formula computation is very expensive. But you do a little algebraic manipulation play, you get into this formula. Later, when we study data warehouse, you'll find the computation effort for the formula like the later one is substantially smaller than the original one. Why? You probably can see it. Why this one is substantially smaller in the computation cost? You know, for computers, you can incrementally add things. You get a new point, you add it in. Okay, incrementally add it in. You probably can see this one essentially is the sum. This one is the sum of the square. Okay. You get a new data, you get a new piece of data. You add into this one. It's very easy because you get the sum. You add one, it just add you up, right? This one said I originally get a, square sum, the sum of the square. You add one more, you just square it, add it in. It's extremely easy. For a computer, it almost takes no effort. But here you have to, you have to start computing a little trickier thing, right? So you probably can see this is cheaper. And later, when you really implement it, you will see there is a big difference. Even they are, mathematically, they are identical. Now we look at the graphical display, because we know one picture worth 10,000 words, right? You watch it. It's much easier than you count it. You look at all the pieces of data. How to watch it? There are many ways. One popular way called box plot. Okay. Another one called histogram. Then we have quantile plot, quantile plot, or scatter plot. I just wonder, okay, I just wonder your knowledge. How many people know box plot? Okay, we got not too bad. We got about 1/3, I think. How many people know histogram? Yeah, I think almost everybody knows histogram, right, because you see it. So then I think it's easier. I probably just explain a little more on box plot. Then we get into the others. Okay. Box plot is very popular used, especially in statistics. Okay. But even nowadays, you go to any data warehouse. Okay. For example, I remember early days, in Canada, in Ottawa, they have one software called PowerPlay. They have a company later acquired by IBM. Okay, and they actually use the box plot very popularly. And I talked to them. They actually said, the people are actually very, very interested in not just the box plot, but they interested in the outliers. Okay, how they do this, I probably can tell you. You can see how to do box plot is you get the data. Of course, you have to first sort it. Okay, you don't sort it, you won't get box plot. You sort it, you compute quantiles. Essentially, more exactly, you compute the quartiles. Quartile means where is the 25 percentile, whereas the 50 percentile, of course, we call this 50 percentile is the median, and where is the 75 percentile. Okay. If you sort it, the things right in the 25%, that's the 25 percentile, right? And then they draw a box. Okay, for this box, the lower box, okay, this box, the bottom of this box is Q1, is quantile 1. We say 25% the quartile. Okay, that means the first quartile, or I say 25% percentile, okay, or quantile, okay, something. You can say this is Q1, this is a median. Usually some people also draw a point as to where the mean and median may not be overlaid, right? Only symmetric one you overlay. Then this is Q3, this 70% percentile, okay? 75% higher. You get this Q3, Q1, this median essentially Q2. You draw this one is your box, okay? Then you, of course, once you sort it, you get a mean and a max. Originally you got it. Then you stretch. Using the line you stretch. Stretch one, we call this one as a whisker. Of course, those whisker, you can write a solid line, many write a solid line plus dotted line. Okay. Solid lines, sometimes they extend to 90%. Of course, depends on your application, you can extend to 95%, whatever. Okay. Suppose you extend to 90%, this one extend to 10%. the remaining two things at the bottom, they don't draw solid line, they draw dashed line, or they put outlier there. That means which point is the outlier. Okay. You suppose you go down to, say, Microsoft. Okay. The Microsoft CEO or Bill Gates. Okay. Maybe their salary really high. Okay. So the very high end is beyond this whisker 90 percentile. So this could be 95 or 99, those ones. Actually, the company told me that their software once it got released, most people look at this box plot. The most interesting one is they click those outliers. Because you get a salary, they see who's top one salary, top two salary. They look at those outliers. So, but box plot is very nice representation. Okay. If your box plot is very fat, that means actually the spread is very, very low, very small. But if your box plot is very thin, that means the spread is very, very big. Right? So this is a typical one. And this box itself, they call interquartile range, or they call IQR, that which essentially Q3 minus Q1, you can see. So this box plot is very, very visible, very telling. You just watch it, you actually see a lot of things. So most people say outlier is higher and lower than 1.5 times IQR. Of course, it depends on different applications. You can define the outlier range in different ways. Right? So these are the, even I think in those software, you can define what is how long your whisker want to extend, and how do you define the outlier. So this is just a software. You can see there are lots of different box plots. This is like a 3D box plot. You have every dimension, you have a box plot. That means within this range, you sort that data, you can get a box. Histogram is also very popular used. Based on our voting, I think most people know what is histogram. The histogram, one important thing is usually you sort the data and you partition them into even range. Okay, for example, of course, some may not be strictly even, but you partition them into even range in most cases. Then you base on the frequency. Within this, how many times it appears, you give the bar how high it is. So that one you get a histogram. Okay. But a histogram is different from bar chart. If you do Microsoft Excel, you say, I want to see bar charts or pie charts. You click a button, you get bar charts or pie charts. Bar charts looks like histogram, so they are different. What are the differences? Bar charts, all these bars may or may not have order. You think about this. Okay. But suppose you get bar charts, you say, oh, this bar is Asia, this bar is Europe, this is North America, this is South America. You get this. Okay. You can change the order, what order you want to show. You say sort it alphabetically, or you put America in the front, or you put Asia or Australia in the front, whatever. It doesn't change any semantic meaning. Right? So that one is a bar chart, because a bar is what you define is, in most cases, it's nominal, it's the name. Okay. But a histogram, this part of value are sorted. Okay. Of course, you can chop them, thin and a little wide, a little fat. But that's still different from bar chart, right? If you can see. I actually wrote down what are the difference between bar chart. I think it's common sense. You just read it. Okay. I believe you play bar charts or histogram all the time, especially if you play Microsoft, say Excel or any other software online. But one thing I really want to mention is histogram often tells more than box plots. You look at box plots is very useful, but I just give you this two simple pictures, two histograms. What my intention to draw these two very strange histograms? Okay. I just show how do you draw box plots, you can imagine. If you draw box plots, you got the same box plot, believe it or not. Think about this. Okay, you can see these two. Where is the median? Watch medians here, this medians here. They have the same median. Right? Where is the 25 percentile, or Q1? Look at the Q1 is somewhere here, this Q1 is somewhere here. Right? Q3 somewhere here, Q3 somewhere here. You actually can see this histogram shows this has a very different distribution. But once you draw the box plot, it may fool you. You can see the same box plot. Right? That means box plot is nice, but histogram, the picture is a little more complicated. The histogram tells you more, right? So that's why, you know, even a lot of statisticians show the box plots, which is very nice. But sometimes you really want to show the histogram because you can tell more. Okay. So that's the things you want to know. Another one is a quantile. Quantile actually says you get distribution. You sort the data. Then you can either draw, for example, you can draw the data in a real way, but another one is you can draw the data in a quantile way. Say, at what point you cover 60% of your data. At what point you cover 80% of your data. That's quantile. Okay. For example, suppose we get a class distribution. Okay. There's one way is you show in the histogram, you show how many people get 10 to 20, how many get 20 to 30, or some people get 90 to 100. Okay. But another way I can draw the quantile is at what point this score covered 60% of the class, or what score covered 80% of the class. You can draw this quantile, right? So this is the quantile plot. That means shows this one shows a percentage of the one. Okay. And you can even draw the QQ plot. QQ plot means you get a 1 is a distribution along one dimension, another distribution along the other dimension. Then you look at the distribution. You can draw this QQ plot. I think I probably should go to Google Image and try to give you better pictures because those things, you know, does not show that much on the quantile. Of course, it does show, but you may get a little confused that this $120 has anything important. This is just to say $120 is the highest price probably in the Walmart charge something, right? Then you get one. So it doesn't mean it's 120%. This actually is the 100% of your data. So 120%. Another one is scatter plot. I believe you probably saw a scatter plot in many cases. Scatter plot means you get a data like this is the price, this item sold. You get the concrete data, say this price, get this 300 things sold, you put a dot. Okay. Then you may, this scatter plot, you may put dot across your map all the places. Depends on where the data really distributed. Right. So that means this is your price, this is the number of items sold. Then if you want to, suppose you are dealing with Amazon, okay? Amazon, some may sell less than $1, the other may sell $1,000. So you get a big one. Then you say item sold, you can plot it anywhere. So then you get a big scatter plot. Why do you use scatter plot? Because you actually can see the distribution of where's the highest one, where's the lower one, but they may not be very regular. So you use slot, you use scatter plot, you actually see the whole picture somehow. Right? For example, you want to see correlation or something. You whether the higher one will sell more. You draw it, you see the distribution like a correlation. You say, oh, it's a positive correlated. The other one could be negative correlated. You get cheaper, you sell more. You get more expensive, sell less. You get negative correlated. You look at scatter plot, you can see it. Yeah, that's exactly I'm showing you the correlation. Watch the scatter plot. Of course, we'll give you a formula how to compute it. But you can see this scatter plot shows positive correlation. Because if you assume this is the price, this is the item sold, it means you raise the price or the price are high, you actually sold more. Right? This is positive correlated. This one is negative correlated. Means the price high actually sold less. So this is negative correlated. What about this one? You say, oh, this one is not correlated at all. Actually, a lot of people want to be a little more serious. They say, okay, this one is not absolutely not correlated. Because if you chop things in the middle, you chop these things in the middle, you say this first half actually is somewhat positive correlated. The second half is somewhat negative correlated. You form like a, like a wedge, right? So it's clearly, it has some regularity, right? And what is uncorrelated at all? You look at those pictures. Okay. This picture says, it almost a point scatter all over. You can hardly draw any line, positive or negative. So this one, you can clearly say this is not correlated. What about these two? These two still not correlated. Just the difference is here you have a price range, right? You think about it. Your lowest one, suppose, is $10. The highest one, suppose, is $50. So you look at the scatter plots, they are around this range. There's nothing below 10. There's nothing above 50. But it's still not irregular, right? It's uncorrelated. This one actually says, this you can think is items. This is a price. No matter what, you will see these are uncorrelated. They just restricted some part. Right? This is still uncorrelated. So watching the scatter plot is very, very, telling in the sense you will know the data have any kind of regularity. Right? Now we come down to data visualization. That means you got data. I already show you the plot, the scatter plot, the quantile plot, all these things. But actually, people want to see the data in a more vivid way, right? So the more vivid way, you need to go to the graphics course or something if you want to produce software. Okay? Actually, if you are interested in, I think we have an online Coursera course offered by UIUC. We have a data mining specialization. For the whole UIUC, they have 6 courses. Okay. One course already released in the summer is data visualization. That means, actually, it was done by Professor John Hart. He is a graphics person, graphics professor. That's the expertise. It's not like we are an analytical person. We play with numbers. They play with pictures, graphs. Okay. So why the data visualization is very useful for data mining? The first important thing is people already said one picture was 10,000 words. Why one picture was 10,000 words? Just because the human eye is a very, very powerful computer, if you think that way. It's a very fast processor, right? Plus your brain, you can think about it. So you can gain insight just by watching the picture. So you map data into some kind of graphics, you actually can see a lot. You understand a lot. That's why the first important thing is that data actually can be visualized, can be viewed. And you provide a qualitative overview. Like I said, correlated, not correlated. Of course, I can give you computer correlation coefficient, but that efficient doesn't tell you the vivid picture. If you watch the data, you actually got a much better feeling, right? So that's why you get a qualitative view. You can search for patterns, trends, structures, relationships like a correlation, or irregularities like outliers. You can easily see it, right? And help you find interesting regions, even the parameters. Okay? And it's also a visual proof of your program, of your something works. Right? You think about this. If you, in many cases, you want to do debugging, if you can view something in the picture, actually debugging sometimes becomes much more effective because you immediately understand where's the problem, right? You think about some software engineering can even map your execution trace into some picture. You see where likely it goes wrong, right? So those are the things you like to see. And visualization have many, many tools, many, many methods. We are going to show you something. Even I'm not going to teach you how to program it. You want to program it, you take a graphics course or go to John Hart Coursera course, right? But his data visualization teaching you how to program it to do visualization. Okay, so I'm going to just show you how to appreciate it, how to enjoy it, right? So that's a pixel-oriented, geometric, projection-based, icon-based, hierarchical ones, and also there are ways to visual very complex data or even networks. So I first show you the pixel-oriented visualization. Pixel-oriented organization is you got lots of different dimensions. For each dimension, you will be able to sort the data and map the data in some way, getting into something like this. Okay. For example, you can sort income. Okay, then you can map them down there. And here, if you see this, you may say using the dark one means there are more people, more counts. The bright one means less counts. And here you probably see income, you say, oh, the low income people has more people, but it gradually reduced to the high income. The credit limit, the same thing. But if you watch the transaction volume, you probably see the transaction very small number and very big number is small, but actually doing the medium-sized transaction actually quite a lot. Then you see the distribution. But if you look at the age, suppose this age, if you sorted it, look at the transactions, you probably see there's almost any age they do the transactions, right? It's quite scattered now, right? So you will see there. Sometimes you see the trend, sometimes you may not see the trend, but that's also very telling. But those pixels usually won't see this way because it's not a very, you get all the dimensions, you take every dimension, you look at this. This is not a very telling, right? There's some nice way you can organize them, then it becomes better. Actually, for pixel-oriented, people developed many different ways to visualize it. You don't want to visualize in a parallel. I give you 10 dimensions, you get 10 columns. You want to visualize in a more vivid way. The more vivid way is this way. Okay. For example, you got 6 dimensions. You don't want to get 6 bars, right? It looks very dumb. You get one circle. You partition them into 6 dimensions. Then you arrange them in some organized order way. Then that will see the correlation or see each dimension how they spread, will see much better. So that's the way most people, when you say picture-oriented, they actually map into circles. They get into circle segments. Later, I'm going even to show you in visual data mining, like a visual classification. Some people do classification using deep learning, using a lot of computation. But there are some people, they do data mining by mapping this into this big circle. They just watch all the different dimensions, see which dimension is more regular. They know where to pick up the dimension to split them into trees. Okay. So that's visualization, the power of the eyes, right? So you can see this one is the one actually was done by a PhD student early days in Germany, University of Munich. What he did is he got so many dimensions, like 40 different dimensions. He does not know which dimension is more relevant, and he wants to view it instead of computing those entropies or information gains or all the different measures. He just say, I map the data into pictures. I watch it to know which dimension is better. How he watch it? He watch it, he say, which dimension, different colors means different classes, different class numbers. For example, you just think about it. If you say, you are going to buy this product, or you are definitely not going to buy this product, or if somehow I may buy this product, you may map into 3 colors. Okay. Once you get different colors, they map this into a picture like this. Okay. And which one is better to split things, which one is very messy? You just watch this, you can see which one the color is very uniform. Okay. until certain points they spread. He says, oh, this one, actually, I know this one, if I cut it here, I take this one, cut it here, this one is almost in one class. Right? So if you think about it, you say, who is not going to buy? I'm not going to send ads to those guys. Okay? If you see those green ones, means they're not going to buy. You pick this dimension out. This dimension may be income, or maybe something like a vacation weeks or something. You pick it up. There's anything below that, don't send ads because you are not going to get anything. Right? So that's a nice thing to do classification. That's visualization using this way. You can see. Very useful. Right? So this one, actually, you can see, this is representing 50 dimensions of data item because you have a 50 charts. You cut your watermelon in 50 slots, right? That's a 50. And it represents 265,000 data items. But those data items organized this way become so nice to see. Right? It's not a painful to compute it anymore. Right? So that's a nice way to do classification, right? And there are other geometric methods. Okay, the geometric methods, we have direct visualization. I'm going to show you, and we have a scatter plot and a scatter plot matrices. I just show you scatter plot. Later, I'm going to show you many dimensions they can stack together, get many scatter plots projecting one plane. You can see it. And we have landscape, we have projection pursuit technique. We will have hyperslice parallel coordinates. I'm not going to show you everything, but I pick up something I'm going to show you. You probably will see it's quite interesting. Okay, this one actually was done by our next door, NCSA. If you go to NCSA, the ground floor, you will see lots of pictures. Those are pictures generated from data. Okay. All those pictures, very nice pictures, actually was a data visualization pictures. Okay. Actually, before I came, I was in a meeting. One leading one is Colleen. She actually was the expert at NCSA doing this visualization. We were just this meeting UCLA Medical School. We were discussing some projects. Okay, before I walked down. Actually, what they do is doing this visualization. This visualization, you can see, is based on twists based on vorticity. Okay, they actually have the earthquakes, they have hurricane pictures. Those are direct visualization. Lots of data you can put them in a 3D or 2D way. Okay. This one is a matrix of scatter plot. We call scatter plot matrix. What does this mean? This actually, you have many dimensions. You can see here, you get 4 dimensions. You get a longitude, latitude, depth, and this is the value. Remember, you get 4 dimensions. You get a 4 by 4. You can think about this. Longitude and latitude getting together, you can get one dimension. You get one scatter plot. Of course, longitude, you also can get a scatter plot. The longitude scatter plot is always a line, a center line, you can see, because longitude, you get the same number. You just get number. In the middle, you don't have it, right? You get the straight line like this. Otherwise, this is longitude matches latitude. This longitude matches depth. This one matches the value. So you get 4 variables. You want to all view them in scatter plot way. You get a 4 by 4 matrix. This matrix actually gives you 4 by 4, 16 scatter plot down here in one plane. You actually can have much better understanding on the data distribution and their mutual relationships. So this scatter plot matrix has been used very popularly because you can see the many scatter plots and their mutual relationship in this way. Actually, you probably can see there's something symmetric. You can imagine it should be symmetric, right? Okay, this is a scatter plot matrix. This one is a landscape. Actually, this landscape is news articles. They try to visualize so many different news articles with certain keywords appear more frequent. They actually get a little red, a little high on the altitude. So you cannot see it. This one is the police. This one is talks. This one is soldiers. No, you get many articles. You try to map them to see what different kind of words and how they distribute it. Of course, you have to compute in a little tricky way to map different words in different coordinates. But based on their frequency, you can draw 3D like mountains, and also based on you can see different words appear in the same article or in different articles. You can draw them in different colors. So those colors and heights represent a lot of things you want to represent. This is visualization using the landscape. And those green background, the blue background means that the word did not really appear, right? Then there's another interesting way to do is parallel coordinates. What are parallel coordinates? You do have a few dimensions, okay? You can see, for example, this one is a visualized Fisher's iris data. Actually, this data, I think, is in UC Irvine. They have a machine learning website. The people donated a lot of data. Okay, one data is Fisher's iris data. Of course, there are many, hundreds of them. Okay, this is one data package. Then they have those flowers. They have a width, length, and another is petals, width, and length. So you get a sepals width, length, a petal width, length. Then you have different flowers. Okay. Then for each flower, you have one point. They link, but the width linked to the length linked to the petal width, linked to the petal length. So you can see, you can link them. Each flower you can link in that way. So you get so many, you can link in many ways. Then you got this one called parallel coordinate. Why parallel? You can see each one is a dimension. And those are the values. Like this is the width, this is depth, those are the values. And each object is one line penetrating all the dimensions, right? So once you map them in this way, you actually can see there's some, for example, you can find some regularity. Like this, the red one means if the sepal width is pretty high, but the length will be lower, and the petal width will be even lower, right? You can watch this. You got lots of insights. So this actually is a parallel coordinate. If you got a relational database, you think about this. Okay, you get all these different values. Each dimension is one attribute. You get 10 attributes. You get 10 those parallel coordinates. Then you link. This is the object. For example, a student taking this course likely get this score, or taking the other course likely to get the other score. You get each student. You can plot them. You may say, oh, the A students may actually get a B in this one, right? So, but the F student probably get F all the places, right? So those are the things you can easily watch, right? So those are the usefulness of the parallel coordinates, and you actually have a way to visualize them. Like this one, you can see this is a visualization of parallel coordinates with thousands of data you can put them. But you do see a lot of irregularity. It's not a mess, right? Because the data higher, map them higher or lower, so you can easily see. So how to work out parallel coordinates is very simple. Right? You probably just watch this, you can see. You can, if you were doing computer graphics course, this is probably the easiest thing you can plot. Right? Okay, so I think later there are many other visualization things. I'm going to do it in the next lecture. Okay, thank you. Yes.
I'm a graduate student in Hongkong, so can I my credits?
Sure. What you need to do is you send me it. I better tweet this, get it out.